It was a beautiful night. Both moons hung low in the horizon, thin red crescents, their feeble light glimmering on the ocean. The sun, a disk of orange that dominated the sky for weeks at a time, had finally dipped below the rugged hills to the north. The heat of high summer had passed, the evenings were no longer a humid swamp, and the sky was now ablaze with the light of 50,000 stars. All the familiar constellations were present, as well as hundreds more that only the most ardent of astronomers knew by heart. Suddenly, one of the stars began to brighten. Onlookers watched in delight as it grew and grew in intensity. This was no cause for alarm. Generations ago, they had deduced that this was a cosmic explosion, the triggering of the death of a nearby massive star. But despite their advanced knowledge, they still preferred to call these events by their traditional name: a guest star. The guest star quickly outshone all of the others in the sky, becoming even brighter than the dozen planets of their system. Before long, it was brighter even than the dual full moon. Parties broke out spontaneously across the globe. Guest stars were common, occurring roughly once a year, but this was sure to be one for the record books. But as most people celebrated, one observer looked on in consternation. They were tasked with monitoring wind patterns in the upper atmosphere. A few of their satellites were providing real-time information, and their measurements indicated a dramatic drop in ozone levels, in perfect conjunction with the increasing luminosity of the guest star. If this continued, it appeared that they would lose their protective ozone layer in less than a week. Though just a story, there is no doubt that were a guest star to appear so close, a supernova, it would spell the end of any civilization. And in this case, on one of the first worlds to arise in the cosmos less than 1 billion years after the Big Bang, supernovae would have regularly speckled the already crowded night sky. The early universe was an active, fertile, and violent place. At that time, galaxies would have been still forming, bursting at the seams with round after round of intense star formation. And while these explosions enriched the interstellar medium with the heavy elements needed to fashion rocky planets and possibly life itself, they also posed a tremendous risk to any life that emerged. And so, when did those worlds first emerge, and what were they like? How can we know what variety of planets there are out there, both in the modern day and distant ancient cosmos? The journey to the first planets will take us through an uncountable variety of wondrous worlds, from great blue Jupiters with atmospheres of raining glass, to tiny frozen rocks teetering on the abyss, and may even give us hints about the mystery of alien life in the universe. The Europa Clipper space probe launched on the 14th of October and will use gravitational assists from Mars and the Earth to arrive at arguably Jupiter's most interesting moon in 2030. Of course, if those gravitational assists are misjudged even slightly, then the probe could spiral off into oblivion. Precision is hugely important when exploring the universe. This video has been sponsored by Novium, and their hover pens are a fantastic, classy gift idea and one that reflects the importance of precision and smart design in space exploration. Crowned one of Time's best inventions of 2022, the Novium hover pen is a stylish and eye-catching ballpoint pen that hovers at a 23.5-degree angle, just like the Earth's axial tilt, without the aid of electricity, just using gravity and neodymium magnets. It can freely spin on its base, is crafted from aircraft-grade aluminium, is refillable, and provides a comfortable and smooth writing experience. Designed by an actual physicist, the hover pen is inspired by outer space, and the premium version even comes with a real shard of the Myon-Yonah-Luster meteorite embedded within it. It's the perfect gift for space aficionados, and they also have a new edition which combines a rollerball and fountain pen into one sleek package. So, click on the link in the description or use the QR codes on screen and use the code HOTU to get 10% off any hover pen and free shipping to most countries including North America, Europe and Australia. There may be an alien civilization right around the galactic corner, or at least the beginnings of one. It may be on a planet not unlike our own, a water-rich world orbiting a yellow-white star. It may be something far different, like a parched moon of a gas giant hugging the limits of habitability around a red dwarf. But it's unlikely that the signs of life will be obvious, otherwise we would have seen it by now. Instead, they will be subtle, mere shifts in the spectrum of light, something that only a super telescope of the next generation will be capable of detecting. And so Courtney Dressing knows that she has to get this right. A professor at the University of California, Berkeley, she was tapped by NASA to co-lead the initial development stages of its next flagship mission, a telescope so ambitious it will make the James Webb pale in comparison. Currently named the Habitable Worlds Observatory, the telescope itself won't be launched for decades. According to Dressing, if it were to be imagined as a 100-meter race to launch, we would be putting on our shoes. But the Habitable Worlds Observatory won't just be a planet-hunting telescope. It will be humanity's first serious attempt to search for life itself, and will do so with an unfolding mirror several times larger than Webb. With that kind of resolving power, it will take pictures, actual images of dozens of nearby Earth-like exoplanets, and will have the resolving power needed to search for biosignatures or traces of elements hinting at the presence of life in their atmospheres. While current telescopes like the James Webb can perform similar kinds of observations, they are limited to only giant planets. This new super telescope will instead target Earth-like worlds, small, rocky planets. It is the future of space telescopes. And so how far we've come in a mere 30 years. For centuries, astronomers had assumed that strange alien planets orbited other stars. It's not a huge leap in logic. Our Sun is nothing special, neither extremely small or extremely large, and so there should be nothing special about the appearance of planets in our own solar system. Thus, any average star should probably have planets. But what kind of planets, and how many? Does every star, of which there are hundreds of billions in the Milky Way galaxy alone, have a planetary system? And if it does that system look like ours, with a quartet of rocky planets and a quartet of giants? Is Jupiter the largest possible and Mercury the smallest? And yet, as astronomy advanced into the late 20th century, the vast majority of astronomers believed that it was a fool's errand to go hunting for other worlds. According to Princeton astronomer Josh Wynne, exoplanet hunters in the 1980s and 90s worked in an atmosphere of skepticism bordering on hostility. The main issue was finding them. Planets may seem large to us. Our own Earth is so vast that its curvature is barely perceptible, but they are nothing compared to stars. Our own Sun could swallow the entire Earth over 1 million times and still have room for more. The largest planet in the solar system, Jupiter, weighs less than 1,000th the mass of the Sun. Indeed, if you were an astronomer viewing the solar system from 10 parsecs away, Jupiter and the Sun would appear to be roughly half an arcsecond separated from each other. That's roughly the same visible diameter of a small coin, sitting several kilometers away from you. And size isn't the only difficulty when hunting for planets. If an object is luminous enough, it can still make itself visible and known to astronomers. Take neutron stars, for example. They are no bigger than a typical city, and yet they blaze so intensely they can be seen from millions of light years away. But planets don't have any advantages here either. The Sun is roughly 250 million times brighter than Jupiter. And so when the first confirmed exoplanet was discovered in 1992, it wasn't by any sort of traditional astronomical technique. And the planet didn't orbit any traditional kind of astronomical object. Two astronomers, the Canadian Dale Frail and the Polish Alexander Wolszczyn, announced an unexpected discovery. 2 planets orbiting a pulsar. Not a nearby star, not a mid-sized star, not any of the usual suspects. one of the strangest objects in the universe. A pulsar is a kind of neutron star that blasts beams of radiation into space as it rotates. They are arguably some of the most extreme objects in the universe, second only to black holes. At only a few kilometers across, they are relatively tiny, yet due to their crushing gravity, the tallest mountains on their surfaces are only a few millimeters high. And if you fell from one, you would reach half the speed of light before you hit the ground. The fastest pulsar spins at tens of thousands of revolutions per minute, and the pulses they release contain photons with energies 10 trillion times stronger than visible light, flooding their surroundings with deadly radiation. And yet PSR B1257+12, sitting over 2,000 light-years away from the Earth in the direction of the Virgo constellation, seemed to have a planetary system. Although Frail and Volchan managed to find evidence for them not by studying the system directly, it was much too far away. Instead, they used subtle variations in the pulsing signal from their host star. Planets do not have much mass compared to their parent star, but it's not zero. Whispers of gravity can be felt from even the weakest of sources, and so as planets orbit their parent stars, they gently tug at them, causing the star to wobble ever so slightly. This causes, amongst other things, a Doppler shift in the light coming from the star. The physics behind this is the same as the familiar rising and lowering of pitch of a passing ambulance. When the star is moving towards us, light gets squeezed to shorter wavelengths and higher frequencies, while the opposite happens when the star is moving away from us. Pulsars make for exceptionally delicate instruments for measuring Doppler shifts, because their pulses are incredibly regular, flashing away on our sky with a regularity, cadence, and perfection of rhythm that compete with our own atomic clocks. As for Frail and Volchan, after they accounted for the motion of the Earth and the Sun, the delay in timings due to the pulsar's radio emissions traveling through the interstellar medium, and the occasional glitch where the pulsar suddenly and unexpectedly switches frequencies, they found a Doppler shift that could only be explained by the presence of two orbiting objects, each with a mass roughly 4 times that of the Earth. And after a naming competition held by the International Astronomical Union in 2015, humanity's first 2 known exoplanets are now known as Poltergeist and Phobator, a beast-like character from Ovid that appears in dreams. They are joined in this strange system by their sibling Draga, named after undead creatures from Norse mythology and discovered in 1994, which is currently the smallest known exoplanet, at less than twice the mass of our Moon, a testament to just how sensitive pulsars can be as exoplanet detectors. And the names are fitting. Pulsars are undead stars, the leftover cores of once bright, living suns that still emit leftover radiation. And so it wasn't until 1995 that astronomers found their first exoplanet orbiting a sun-like star. That discovery required much more precision, determination, and outright luck. My reaction was that it must be wrong somewhere, mused Swiss astronomer Didier Queloz of Cambridge University, Nobel laureate and one of the discoverers. I was a little bit ashamed to communicate this potential error to my supervisor because I thought I'd made a mistake. But he had not. Working with his research advisor and future Nobel co-laureate Michel Mayor, Queloz found the first hints of a reliable signal in the shift of radiation coming from 51 Pegasi, an unremarkable sun-like star sitting about 50 light-years away. But the data implied something truly bizarre. The signal implied that the planet was massive, roughly the same mass of Jupiter, but orbiting far too close to its star, just a mere 0.05 astronomical units, 1/8 the distance that Mercury orbits from the Sun. It would take years to convince the astronomical community of the validity of the observation, a condition that Queloz regarded as requiring a soft insanity to persevere through. And yet it would turn out that nature is far stranger than our imaginations, especially when it comes to exoplanets. And in the years since that momentous discovery, astronomers have developed an array of techniques for finding exoplanets and analyzing them, many even more bizarre than Frail and Volchan's pulsar planets, or Queloz's mammoth, close-orbiting world. Take, for example, the planet HD 189733b, a gas giant 10% heavier than Jupiter, roughly 65 light-years away. Unlike the orange and yellow hues familiar to Jupiter, this exoplanet has a deep cobalt blue atmosphere, and that atmosphere is deadly. An umbrella wouldn't help you here. It rains glass sideways with winds up to 7 times the speed of sound. Or take TRES-2b, the darkest known exoplanet. Sitting roughly 700 light-years from Earth, this exoplanet is exceptionally dark. Initial estimates suggest that it reflects less than 1% of all the light hitting its surface. Despite its vast size, it's larger than Jupiter. Whatever its atmosphere is made of, it's capable of absorbing almost all visible light. A close-up approach of TRES-2b would seem like landing on the surface of a black hole. And then there's J1407b, the super Saturn, located 450 light-years away. A gas giant, this exoplanet hosts a ring system that would put Saturns to shame. Orbiting J1407b are over 30 individual ring systems, each one millions of kilometers across. All combined, the rings span a diameter of 180 million kilometers and contain an entire Earth's mass of material, making it over 600 times larger than Saturn's. The rings utterly dwarf the planet itself. And so picture in your mind the wildest planet imaginable, with whatever fanciful composition and orbit you can dream of. Chances are that this planet exists, and thousands more beyond. But when it comes to discovering new exoplanets, alongside the Doppler shift method, more properly known as the radial velocity technique, the most powerful scheme is called the transit method, and it involves nothing more than staring at a star for a long period of time and waiting. Planet hunting with the transit method involves searching the heavens for tiny eclipses. If a star hosts a planet, and the plane of its orbit just happens to line up with our point of view, then occasionally the planet will cross in front of the face of its star, temporarily blocking a small amount of light. This effect is minuscule and relies on pure luck, but if you stare at enough stars for long enough periods of time, you'll eventually detect the telltale sign of a planetary transit event. And in 2009, NASA's Kepler Space Telescope became the world's premier planet hunter. This telescope continuously observed roughly 500,000 stars in the direction of the constellation Cygnus, searching for signs of slight dimming. That mission alone produced a treasure trove of nearly 3,000 confirmed exoplanets and thousands more candidates. Even one of the very first planets found by the Kepler Space Telescope was full of wonders, something ripped straight from science fiction. Kepler-16b is a gas giant with a mass between Saturn and Jupiter sitting 245 light-years away. What made it surprising was not the planet itself, but the system. Kepler-16b doesn't just orbit one star, but 2, the first ever confirmed circumbinary planet. Sitting on the surface of the planet, you could watch as its twin suns dipped below the horizon in a recreation of the iconic Star Wars scene. But despite the success of the transit method, astronomers need a variety of tools to paint as complete a portrait as possible for every exoplanet, especially in the hunt for the very first in the universe. The transit method is by far the easiest method known to find exoplanets, but it only gives a measure of the planet's radius, based on the dip in the star's light. Astronomers have to use other methods to estimate the planet's mass. From there, they turn to complex modeling to make reasonable guesses as to a planet's composition and structure. For example, we generally know the abundance of elements in the universe and how they interact with each other. If a planet is roughly the same size and mass as the Earth, then it's less likely to be made of light elements like hydrogen and helium, and more likely to be made of carbon, silicon, and water. Kepler's successor, the Transiting Exoplanet Survey Satellite, or TESS for short, uses a variety of methods packaged into one spacecraft to measure as many properties as possible. At present, 6 years since the launch of the mission, TESS has identified 7,138 candidate exoplanets, And in 2024, TESS discovered TIC 365102760b, a planet sitting 1800 light-years from Earth. The discoverers nicknamed it Phoenix, and for good reason. This planet is so close to its parent star that it should be nothing but a roasted cinder, especially after its star entered its red giant phase. But somehow, this world has retained its atmosphere, an incredible and so far unexplainable feat. But astronomers suspect that this act of planetary resistance won't last long, and the world will lose its grip on its own atmosphere in less than 100 million years. The next great planet hunter will be the Nancy Grace Roman Space Telescope, which is currently scheduled to launch in May of 2027. Its unique properties will allow it to create a census of up to 1 million exoplanets in the Milky Way galaxy. But perhaps the most important method of revealing an exoplanet is studying its light directly. During a transit event, most of the light reaching our telescopes comes from the parent star directly. But some of that light is either reflected off the planet or passes through its atmosphere. This contamination of the light is incredibly small, but if we capture a strong enough signal during the transit event, we can isolate the contributions from the planet and measure some of the elements present. For this technique, however, we can only use the most powerful, most sensitive instruments, like the Hubble or James Webb Space Telescopes. Indeed, Webb was designed with exactly this goal in mind, and already it has mapped the atmospheres of scores of exoplanets, finding evidence for molecules such as methane, carbon dioxide, sulfur dioxide, and more. And it is Webb that has shown us that not all exoplanets are grim wastelands. There are also those that show the hopeful signs of life, like K2-18b, a planet sitting only 120 light-years from Earth and first studied in detail with the new telescope in 2023. This world is a sub-Neptune, and a spectrum of its abundant atmosphere shows the faint signatures of methane and carbon dioxide. These elements are certainly possible in a lifeless atmosphere, but also in a life-filled one. And so, our hunt for alien worlds is still in its infancy. And yet even with only a few thousand confirmed detections, we have deduced the existence of worlds that we could not possibly have imagined. The universe is bewildering in complexity and dizzying in its scope, and exoplanets are no exception. As we attempt to plunge deep into the depths of the past to discover the first exoplanets, we must begin by confronting the amazing variety that could possibly exist. The planet is being torn apart before our very eyes. Its parent, however, is fairly normal. A K-type star, slightly smaller and cooler than the Sun, sitting about 66 light-years away. But it hosts a small family of planets in a peculiar series of orbits. A gas giant with a very tight 56-day orbit, roughly twice the distance that Mercury orbits around the Sun, and a second planet roughly the mass of Uranus, sitting even closer to its star, with just a 14-day orbit. And in 2024, a team of astronomers led by Stephen Kane at the University of California, Riverside announced the tentative discovery of yet another body. This was no gas giant but a terrestrial world, 30% wider than the Earth, but clinging to the star in a brutal 2.2-day orbit. Of course, no life likely exists on this planet, no atmosphere, no water. This world is scorched by its proximity to its star, but that's not the only source of its horrors. The dance of the gas giants in their incredibly close orbits means that they exert enormous tidal forces on the Earth-like planet, stretching and squeezing it like putty. The tidal forces are easy enough to calculate, just a simple application of Newton's laws, and it's also easy to calculate how much energy is transferred from the orbits of the giant siblings into tidal deformations of the small terrestrial world. And the conclusion is startling. The constant stretching and squeezing, pulled here and there by the gravitational forces of the giants, releases so much energy that the world itself is glowing, caught in the midst of a perfect tidal storm. With an estimated surface temperature of 2,600 Kelvin, this Earth-like planet is lit up like an incandescent light bulb. But this is no mere speculation or flight of science fiction. This is a sound scientific estimation based on a surprisingly small amount of information and just one example of how clever research can reveal the wonders and majesty of worlds millions of light years away. In almost all cases for these thousands of known alien planets, all we truly know about them is a thin slice of data represented by a line on a plot. But astronomers are enormously clever and used to making great leaps of insight based on meager scraps. Because that line is a spectrum. The concept of atomic spectra was developed in the mid-1800s, before we even understood the nature of atoms and subatomic particles. Indeed, explaining atomic spectra was one of the primary motivations towards the development of quantum mechanics. Each element on the periodic table emits light at a combination of very specific wavelengths, and each molecule does the same. When astronomers look at a distant exoplanet as it transits in front of its parent star, some of the light filters through the planet's atmosphere, and the elements and molecules of that atmosphere each leave their individual fingerprint on the spectrum. And so by examining the spectrum, astronomers can identify the presence of many elements. But it is far from easy. Astronomers need high-resolution data and a raw volume of starlight to get a solid spectrum. And in the often hot and complex atmosphere of alien worlds, molecules can mix together in the same spectrum, especially in the narrow range of wavelengths that astronomers can usually only access. From there, astronomers turn to modelling to build their understanding of these foreign worlds. We understand how physics and chemistry work. We know how atmospheres can react to different intensities of different wavelengths of light. We know how gravity affects the ability of a planet to retain an atmosphere, and we know how molecules mix and dance together in an atmosphere. It does require some guesswork, and statements about exoplanets always up for revision. But through these techniques, astronomers have been able to deduce an astounding variety and complexity of planets within the galaxy. Perhaps the greatest surprise of all was that we were able to detect exoplanets so easily in the 1990s. That's because the first known exoplanets were completely unlike anything we'd ever known from our experience in the solar system. Planets far larger than Jupiter, orbiting closer than Mercury does around the Sun. These worlds are known as hot Jupiters, and they should be impossible. Giant planets can't form close to stars because these planets are made of mostly hydrogen and helium, the lightest of the elements that get easily blown away by the energetic output of young stars. And yet, hot Jupiters aren't just our first known exoplanets, they are among the most common. Astronomers now believe that hot Jupiters start out their lives in distant orbits, but through gravitational interactions and planetary reshuffling find themselves migrating inwards to closer orbits, where they spend the rest of their days roasting alive. Indeed, some hot Jupiters experience such intense radiation that they are bloated and distended, in some cases tidal forces turning them egg-shaped. While hot Jupiters are certainly fascinating, they are unlikely homes for life, at least the kind of life that we know, the kind of life that arises on small, rocky planets in the habitable zones of their stars. But exoplanet surveys have found many such worlds, especially around small red dwarf stars, because those are easier to find with our current techniques. And while we have yet to confirm the existence of liquid water on any extrasolar planet, we have many candidates well deserving of follow-up investigation with the Habitable Worlds Observatory. But we just don't know how many exoplanets exist in the Milky Way. At a bare minimum, we suspect that there is on average one planet for every star, but many estimates suggest that planets are much more common than that, including rough estimates on the number of rogue planets, exoplanets without a parent star drifting through interstellar space. There may be trillions of worlds in our galaxy alone. And so no matter what, despite decades of effort, we've only surveyed an incredibly small fraction of all the planets in the Milky Way. But even with this scarcity of data, we can start to build a rough estimate of the number of potentially habitable worlds in the galaxy, and start to put together a picture of how early in the history of the universe planets could have arisen. And those guesses suggest that if we are searching for life and want to hunt for that life on Earth-sized planets orbiting sun-like stars within their habitable zones, then we may have as many as 5 billion planets to search for. 5 billion chances for life. Our Earth, as unique and special and rare as it is, may have billions of siblings. And the Earth is far from alone. With even the beginnings of these searches, astronomers have been able to discover an astounding variety of exoplanets, each of them completely foreign to anything in our own solar system, smashing the expectations of astronomers from generations past. Besides hot Jupiters and their too close for comfort orbits, there are the circumbinary planets, worlds that orbit 2 stars at once. There are even double planets, objects of roughly equal mass that orbit a common center. If Pluto qualified as a planet, it would likely be counted as a double planet due to its relationship with Charon. There are rogue planets that wander the interstellar wastes, and Trojan planets that follow a larger sibling in its orbit. There are super-Earths and mini-Neptunes, worlds of every conceivable size, larger than Jupiter and smaller than Mercury. There are worlds covered in ice, in lava, in thick layers of hydrogen. There are dry and airless worlds and ocean-covered water planets. There are planets without cores and planets with almost no crust. There are worlds made of an abundance of carbon, or an abundance of silicon, or an abundance of iron. Decades of searches have unearthed thousands of worlds, which represents only a tiny sliver of those in the Milky Way. But even with that meagre sample, we found ourselves continually surprised. It seems that galaxies are enormously efficient at producing planets, and this efficiency may have allowed them to construct planets as early as possible in their histories, and perhaps in the history of the universe. Unfortunately, we do not fully understand the process of planet formation, as it unfolds over the course of hundreds of millions of years. But in addition to fully formed exoplanets, we also have thousands of detailed observations of young stars, protoplanetary disks, and more. We can stitch these collected images together to form the backbone of an overall story, and from there attempt to predict how early planets could have formed in the young universe. Planetary systems like our own begin their lives as diffuse clouds of hydrogen, helium, and a smattering of heavier elements. When these clouds collapse to form a system, most of the material in each of these fragments coalesces towards the center, where friction heats it to high temperatures, becoming a protostar, a star that has not yet ignited fusion in its core. The material eventually forms a flat plane around the protostar, the beginnings of a protoplanetary disk. The vast majority of the disk is made of hydrogen and helium, but sprinkled throughout the swirling chaos is dust. Microscopic grains of heavier, more complex molecules. Just like the dust that clings irritatingly to the surfaces of your home, the dust in a protoplanetary disk sticks together. Finding each other in the spinning sea of lighter gases, the dust begins to clump, molecule by molecule. Over the span of hundreds of thousands of years, these clumps become large enough, roughly 100 meters or so, to completely change the fate of the disk. At roughly this size, the clumps, now known as planetesimals, have a gravitational pull of their own, which they use to inflate their size by attracting new material. Within the inner regions of the disk, near the young star, which has finally begun fusing hydrogen, the heat is too much for light elements like hydrogen and helium to remain, and too much for volatile elements, like water and carbon dioxide, to stay as solid ices. Only the heavier elements, like iron, carbon and silicon, and their molecular combinations, can survive here. The inner regions of a solar system therefore become the home of terrestrial worlds, and the outer regions form the larger, gaseous worlds. And this process, repeating generation after generation, star after star across the nearly countless billions, fills each and every galaxy with a population of planets. So with this picture in mind, It seems that heavy elements are a prerequisite for building planets, and even though planets are numerous, they are small. The Earth, or Jupiter, or any exoplanet may seem enormous to human scales, but they represent mere rounding errors in the cosmic accounting of elements. It is clear that once there is even a small amount of raw material, the simple physics of the universe will give rise to a planet. But how long did it take for the cosmos to generate enough raw material? Planets do not fare well in the face of a dying star. And the small, rocky world precariously close to the guest star as it went supernova was no exception. First came the flood of gamma-ray radiation, stripping away the ozone layer which for billions of years had protected life on their world from the harmful UV radiation of the sun. The oceans overheated, and plants and algae could not withstand the radiation, tearing apart the heart of the food web. Then came the high-energy particles known as cosmic rays, ripping through the planet's magnetic field and showering the surface with deadly energies. Cancers of all kinds across all species spread like a global pandemic. And then, centuries later, civilization long crippled, came the final blow. A shockwave, weakened as it expanded out from the initial explosion, but still powerful enough to tear the atmosphere of the planet away like dandelion seeds in the wind. Had the supernova that claimed their homeworld been any closer, then even the mantle and inner core might have been evaporated in the ensuing blast. As it was, the planet they once called home was just as dead. A barren husk of rock, its once verdant lands and abundant oceans, now dust on a frozen breeze. The young universe was not friendly to life. Billions of years ago, the cosmos was much smaller than it is today. Galaxies were much closer together and they collided with each other much more frequently. Stars formed at an intense rate. Indeed, some galaxies produce stars thousands of times more often than the Milky Way does now. And as those stars formed, they also died in magnificent and frequent supernova explosions, irradiating their vicinity and posing a serious hazard to any life that managed to find a foothold in this hostile era. Thankfully, planets are exceptionally easy to make. The first stars to emerge in the universe were made entirely of hydrogen, helium, and trace amounts of lithium and beryllium, as those were the only elements fashioned in the fires of the Big Bang. They fused heavier elements in their cores, and even more through their explosive deaths, seeding young galaxies with the ingredients needed to begin building planets. And so, although we do not know when this process first began, we do know it didn't take long. Consider the star TOI 561. TOI 561 is a Sun-like star sitting roughly 280 light-years away. As stars go, at first glance it's pretty unremarkable. It's 79% the mass of the Sun and 85% of its radius. If you were to see it with your own eyes, it would look just like any other star, just tinted slightly orange. But TOI 561 isn't just old, it's ancient. It is over twice the age of our Sun, having formed roughly 10.5 billion years ago, right when the Milky Way galaxy was first emerging in its own right. And when TOI 561 formed, the Milky Way wasn't nearly as enriched with heavier elements as it is today. And so, in the awkward nomenclature of astronomers, they classify this star as metal poor. TOI 561 is one of the oldest stars to inhabit our galaxy, and in January of 2021, a team of astronomers led by Lauren Weiss at the University of Hawaii in Manoa announced an unexpected discovery. It has a family of planets. This was confirmed by an independent analysis undertaken by Gaia Laciadelli of the University of Padua. It was no mere fluke of the data. One of the planets orbiting this ancient star is a super-Earth, weighing twice the mass of our planet on a breakneck orbit that lasts only 10 hours. Besides the mysteries of its extreme orbit, the mere existence of this world opens up a confusing question. How did a rocky planet, composed of the heavier elements of the periodic table, form around a star that has barely any of these elements? This question still lingers on, with no clear resolution. For decades, astronomers had assumed that stars and their planets go hand in hand. When a star has a higher abundance of heavier elements, it should be able to fashion more and larger rocky worlds. But it seems that the cosmos has designs of its own. Despite its age, TOI 561 was still able to grow a healthy planetary system with more than enough material for rocky, Earth-like planets. Of course, it doesn't seem likely that the super-Earth that orbits this ancient star is a viable home for life, as it is currently roasting in the ferocious heat of its parent star due to its extreme proximity. But if super-Earths could form around TOI 561 10.5 billion years ago, then it's not a great stretch of the imagination to argue that regular Earths could have formed around the same time. Life first appeared on the Earth almost as soon as our surface cooled and the oceans and continents arose. It seems as if once our planet could support life, it did. And so perhaps some world amongst the trillions yet to be mapped, observed or discovered around a stellar cousin of TOI 561 had just the right combination of elements, temperatures and conditions for life to arise. If that life followed the same evolutionary pathway as life did on Earth, spending billions of years as single-celled organisms, transforming the atmosphere to make it more hospitable and laying down the genetic building blocks for an explosion in complexity leading to the emergence of intelligence, then a star-faring species could have evolved while our own solar system was nothing more than a tenuous cloud of gas and dust floating through interstellar space. Life in the early universe would have been challenging. The cosmos was simply more active and more volatile billions of years ago, resulting in higher rates of star formation and stellar death, soaking every galaxy in more high-energy radiation. Indeed, planets may have quickly formed around most stars, but any life that may have emerged on these worlds would have had to navigate the ultimate catastrophe, the supernova explosion of their own sun. Simulations of planets around supernova suggest that they do not fare well in the face of such enormous energies. At best, the dense nickel and iron cores remain, with everything else, atmosphere, oceans and mantle, evaporating in the blast. And yet, once again, nature gives us a surprising twist. Just like the apparent impossibility of hot Jupiters, planets should not exist around pulsars, which are the leftover cores of giant stars that survived after a supernova explosion. But our very first known exoplanet was found orbiting a pulsar. We do not yet fully understand how planets can find themselves living around a dead star. One theory is that they have always been there, but that is unlikely, since giant stars, the kind of stars that go supernova, are very hot and boil off their protoplanetary disks before planet formation can really get going. Another idea is that planets form around pulsars from the supernova material itself. After initially blasting off at a fraction of the speed of light, much of the material cools off and coalesces around the neutron star, introducing a fresh new round of planet formation. These kinds of ideas highlight just how easy planet formation really is. It can even happen around a dead star. And so we can guess that rocky planet formation happened in the extremely early universe, perhaps within the first billion years of cosmic history, as soon as enough generations of stars lived and died to enrich the interstellar gas clouds with heavy elements. And as for life, while we can't say for certain, it certainly had a chance on these young worlds. Despite the chaos raging through their violent emerging galaxies, planets almost certainly formed that were suitable. Many attempts at life were likely snuffed out by an energetic explosion or gravitational destabilization, but the universe made planets in abundance, and it's very likely that somewhere, billions of years ago, when the first stars and galaxies began to fill the cosmos with light, some creature called one of those primordial worlds home. But so far, we've only considered rocky worlds. Terrestrial planets like our Earth fashioned out of heavier elements with oceans of liquid water. Life may be far stranger than we imagine, and so too might the planets life calls home. if we are willing to extend our definition of planet, we might just be able to push back into the depths of time even further. Arakoth remembers. On January the 1st, 2019, humanity got its first close-up view of a world that had known only darkness. The object was known as Arakoth, a word from the Powhatan language of the Tidewater region of the eastern United States. The language became extinct in the 1700s, but the word is still remembered today, meaning either sky or cloud. Arakoth sits in the Kuiper Belt region of the solar system, a distant and lonely ring of scattered, frozen leftovers from our system's formation. It is small, grey and dirty. Two misshapen lumps of ice and dust roughly 36 kilometers long and 15 to 20 kilometers on a side, glued together by a gentle bump billions of years ago. The object has only ever been visited once in a flyby lasting mere minutes by NASA's New Horizons spacecraft, a project led by Alan Stern and launched in 2009. We only know one face of Arakoth because the flyby did not last long enough to get a full view, and the probe was travelling far too quickly and carried too little fuel to park itself into orbit. But in this little object is written the story of miracles, for Arakoth is incredibly ancient. It was present when the protoplanetary disk of our solar system first coalesced. Escaping to the fringes during the chaotic era of the first planetesimals, it watched as new planets emerged out of the swirling maelstrom, crashing and colliding and forming anew, some being ejected into the interstellar wastes as the survivors, 4 rocky inner planets, 2 gas giants and 2 ice giants, rearranged themselves into a series stable orbit. And Arakoth waited, for billions upon billions of years, knowing nothing more than the dim and distant light of the sun and its feeble but persistent gravitational grip, 1 foot in the solar system and the other poised towards the stars beyond. And then a little spacecraft, no bigger than a piano, sped by, its first visitor in the ages since its formation. But before Arakoth could even register the presence of New Horizons, whether through the slight radar signals bouncing off its surface or the minute deflections of its gravitational influence, it was gone. And so Arakoth resumed its watchful sentry at the gates of the solar system. Arakoth represents not just a lonely outpost in our solar system, it's a tiny clump of dust and ice, far smaller than any planet, barely noticeable in the cosmic scene. But it's much easier for the universe to make small clumps of debris like Arakoth than it is to make massive planets like the Earth, let alone the giants like Jupiter. And objects like Arakoth are more likely to survive any catastrophe that might befall their system, like the death of a giant planet or the imploding of a sun. And so just how early could something like Arakoth form? The objects of the Kuiper Belt are made of relatively simple, common elements like hydrogen, carbon, silicon, and oxygen. Hydrogen was made in abundance within the first few minutes of the Big Bang, so that's easy enough. Carbon and oxygen were fused in the hearts of stars the size of the Sun and larger. Silicon is only made in larger stars, but those stars were exceptionally common in the early universe. The following is pure conjecture, but is based on our latest understanding of star formation. The first stars appeared in the universe when it was only a few 100 million years old. That's how long it took for gravity to do its work on the primordial clouds of hydrogen and helium and collapse them enough to trigger nuclear fusion. It would take many generations of stellar births and deaths to enrich the interstellar gas clouds enough to form significant numbers of planets. But something like Arakoth, or its Kuiper Belt siblings, could have formed much earlier, perhaps within the first handful of stellar generations, before the first galaxy arose, before the first giant black hole arose, when the cosmos was just a loose collection of scattered and lonely clumps of newborn stars, their feeble light flickering for the first time in the lonely depths. one star, somewhere, forever beyond our detection or reach, found itself surrounded by a thin, protoplanetary disk. With just trace amounts of heavier elements, an object like Arakoth could have formed in the cold fringes of the system, the first substantial body composed of rock and ices. The first solid object. While most astronomers do not consider any object in the Kuiper Belt a proper planet, some of them are classed as minor or dwarf planets, and it may have been such a dwarf planet that first formed in an age before even galaxies had evolved. Though it is unlikely that this first dwarf planet could have hosted life. Their own formation depends on ices that can only remain solid far from the light and heat of its parent star. But there is another kind of planet, much larger than any dwarf planet or Kuiper Belt object, that could have emerged in the early universe that might have supported life. These are the Sheehan worlds, a name coined by a group of University of Cambridge researchers as a portmanteau of hydrogen and ocean. At present, these planets are only hypothetical, but astronomers have identified several candidates in the Kepler and TESS surveys. Sheehan planets are massive, approaching the size of Neptune, but most of that bulk comes in the form of thick atmospheres of hydrogen. Indeed, these atmospheres can be thick enough that they maintain enough pressure on the surface that liquid water can persist, perhaps as globe-spanning oceans. They may have formed in the extremely early universe, a relatively small nugget of rock enrobed in an ocean of water, buried underneath a dense atmosphere of easily obtainable hydrogen. But the oldest known planet is no super-Earth or mini-Neptune. It's not a hot Jupiter or a Sheehan world. It's not a fragment or a comet. Its formal designation is PSR B1620-26b, but most astronomers call it Methuselah, after the biblical character who lived to be the oldest person. Methuselah was discovered in 2003 by Stein Sigurdsson of Pennsylvania State University in the globular cluster M4. Globular clusters themselves are amongst the oldest collections of stars in the galaxy, believed to be remnants of galaxies in their own right before they were cannibalized by the Milky Way. Methuselah is a pulsar planet, like the first ever known exoplanet, orbiting a dead core of a once great star. It is huge, weighing over 2.5 times the mass of Jupiter, orbiting around its star at roughly the same distance that Uranus does around the Sun. But its parent star is not alone. There's also a white dwarf, orbiting much closer to the pulsar. While we can't directly estimate the age of Methuselah, we can determine the age of the globular cluster that it makes for its home. And stars in a globular cluster appear at roughly the same time. So while there is significant uncertainty, Methuselah currently holds the record for the oldest known exoplanet, achieving a present-day age of roughly 12.7 billion years. Like all pulsar planets, astronomers aren't exactly sure how Methuselah formed, but given its tremendous bulk and its relatively regular distance from the star, most astronomers believe that Methuselah formed around a Sun-like star in the outskirts of the globular cluster almost 13 billion years ago. The star and its bulky planet then migrated towards the center of M4, and it's there that the planet witnessed a drama unfold before it. The system likely encountered an old neutron star and its companion star, a common denizen of old clusters like M4. Through gravitational interactions, a dance ensued, with the neutron star capturing the wandering star and ejecting its old companion in the process. Once stabilized, Methuselah's star then aged normally, eventually becoming a red giant. Its swollen atmosphere spilled onto the neutron star, transferring energy and angular momentum and causing the neutron star to spin up to become a pulsar, rotating at a rate of 100 times per second. After Methuselah's original parent star exits the red giant stage, it becomes a white dwarf. And after all this drama played out, Methuselah remained for billions of years. However, Methuselah itself is an unlikely candidate for life, at least for life as we currently understand it, just like any other gas giant. But the material to make a planet can also make a moon. And the system doesn't need nearly as many raw heavy elements to fashion a series of moons around such a giant. And so, there is a chance, 13 billion years ago, that some form of life arose in some alien ocean, buried under the globe-spanning ice sheets of a moon around Methuselah. It may or may not have awakened into consciousness, or pierced the ice sheets to witness the drama of its parent star, or the quiet calm of the billions of years since, or the majesty of the Milky Way, visible in all its resplendent glory from the vantage point of the globular cluster. Indeed, if life did find a home on a moon of Methuselah, it would have been shielded by that ice from the cosmic dangers of the early universe, the radiation from supernova explosions, the heat from the red giant star. It could have persisted and even thrived. It may even still be there. The oldest living creatures orbiting the oldest known planet, the end result of a genetic lineage going all the way back to the dawn of stars and galaxies themselves, retaining a memory of a cosmos far unlike our own. If they had eyes and minds filled with curiosity, they could have watched the entire Milky Way emerge and evolve before them. And if they developed telescopes to allow them to peer deeper into that galaxy, they might train their curiosity on a small, insignificant branch of one of the great spiral arms. And in their detailed, careful observations, they might come across a star not unlike the one that once hosted their system. They would find a gas giant, smaller than theirs, but still mighty among its family of planets, and they would detect the thin atmosphere of a water-rich world. And in that atmosphere, the unmistakable sign of that planet's life that has only recently arrived on the galactic scene. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think, and thanks again to Novium for sponsoring this video. Thanks for watching, and we'll see you next time.